Any questions before we start? Y'all know chapter 8 is not due until Monday, so you have time. You have a little bit of extra time, which is good. But then we come back and then we have an exam in a week. Right? It's a week. I think that's right. Soon. It's soon. One moment. Bless you. Okay, so how do you make a mouse smile? Say cheese. Say cheese. All right, so make sure you put your name on the seating chart. And then what I actually want to do is we are going to finish chapter 8 first, and then we're going to do a couple of iClicker questions. So we were almost to the end of chapter 8. But you do need to keep your best friend out because we will be doing some iClicker. So don't lose him. So we were talking about really the solubility of things, right? That's what this whole chapter has been about. But you have to think about when we're thinking about the body, not only are we worried about do things solubilize in a liquid, for example, like blood, but then when and how do they cross the membrane into a cell, right? That's kind of a whole nother ball of wax. So if you're trying to find out if something is soluble, okay, that's great. It is soluble in water, but now is it going to enter the cell? So there are kind of like 3 different ways that things can get into the cell. The first way is through simple diffusion. What's the definition of diffusion? Whatever the molecule is moves from areas of, you move from high concentration to low concentration. So like if you're making a water bottle, right? You have a water bottle and you have some of that squeeze stuff that you squirt into your water bottle, the strawberry lemonade or the peach tea, whatever floats your boat. If you squeeze some in and you don't shake it, what happens? Eventually, if you leave it set long enough, all of those molecules are going to diffuse. They're going to move from an area of high concentration, which is where you squirted it in, to areas of low concentration, like on the sides of the bottle. And the higher the temperature, the quicker this occurs. So this diffusion occurs just because of random movement of the atoms in the substances, right? So the higher the temperature, the faster they're moving. So that's simple diffusion. How does simple diffusion work in regards to a cell? Well, you have to think that in order for something to diffuse into a cell, it has to cross a cell membrane. What is a cell membrane made up of? What's a cell membrane made up of? Phospholipids, right? So we have a lipid bilayer, L-A-Y-E-R, bilayer, a lipid bilayer. So we have those polar head groups and those non-polar fatty acid tails, right? Sort of looks like this, right? So those non-polar tails keep out charged things. Charged things can't get through a membrane. So let's talk about what things can. What things can, just by simple diffusion, move across a cell membrane? Big or small? What do you think? Number one is small. The other thing is things need to be similar to those long fatty acid tails. So those long fatty acid tails are what? Polar or non-polar? Fatty acid tails. They're non-polar, right? The head group, the circle over here, the circle here is polar. So the red is polar. And then the blue are these fatty acid tails. And these are non-polar. So to get through those really long fatty acid tails, the substances are usually really small and non-polar. Now, the exception is water. Water can diffuse across the membrane. So if you diffuse across the membrane, you don't need to be shuttled, you don't need to be shipped, you just go. So for example, gas exchange, right? Every time we inhale and exhale, we're inhaling oxygen, we're exhaling carbon dioxide. Where does that oxygen go? Into the blood, picked up by the hemoglobin in the red blood cells and transported to cells all over the body. But we just say transported to all the cells all over the body because it moves into cells just by diffusion. Because oxygen, O2, look at O2. If I drew O2, how would I draw an O2 molecule? Two atoms of oxygen. How many bonds between them? How many valence electrons in oxygen? 6. So how many more bonds does it need to make to get to an octet? 2, 6, 7, 8, right? 2. So then you end up with, that's O2. So O2 is a small non-polar molecule. So what's going to happen with a small non-polar molecule? It's going to diffuse. And when it diffuses from areas of high concentration to low concentration. So look at that picture. In which direction are those oxygen molecules going to diffuse? Are they going to diffuse in the blue direction or the black direction? Blue. They're going to move in the blue direction because they're moving from areas of high concentration to areas of low concentration. And there doesn't need to be anything there to help them. They just simply diffuse. So there are 2 other ways that things can move across a membrane. So there can be passive diffusion. That's what we just described above, is passive diffusion. You can have facilitated transport. Facilitated transport, this is what I call a tunnel, right? So if you're a car and you want to get from point A to point B, if you go through a tunnel, Does anybody have to open and close the tunnel, move the tunnel? Nothing, right? So it's facilitated in the sense that there's an opening in the membrane. There's a protein that's holding open the membrane, that's allowing things to flow either way, right? But it's just a tunnel through the membrane. If you have something that is active transport, I think of things that are active transport like a ferry boat. A ferry boat, you have to drive onto the ferry with your car or walk onto it, whatever. And the boat has to expend energy to get from one side of the bank to the other, right? Same thing with a facilitated, with an active transport molecule. That protein sitting in the membrane, right? And it grabs this molecule and it pushes it through to the other side. So it actually is active in the sense that it requires energy, right? A facilitated transport is open, is always open. But active, it's actually doing it. So it requires energy. So requires energy, and then tunnel is no energy. So identify the type of transport that would occur. Oxygen. What do we say oxygen was? Small and nonpolar. So what's going to happen? Passive diffusion. Glucose, no energy required. How do you know it's facilitated and not passive? It's not that no energy is required, because no energy required works for both passive diffusion and facilitated transport. So what tells you that it is facilitated transport? Y'all are correct. It's not that big. It's polar. Glucose is polar, right? It's a sugar molecule. What do sugar molecules have all over it? Hydroxides, OH, right? What can OHs do with water? Hydrogen bond. It's a type of dipole-dipole interaction. So you have to have a dipole. You have to be polar for it to happen, right? So because glucose is polar, it cannot go through passive diffusion. It must be facilitated. Okay. All right. Na plus energy required. Is that a small nonpolar molecule? It's small and it's not really polar, but it is what? It's charged. Charged things are not going to get through the membrane all by themselves. They're not. They don't interact with those fatty acid tails very well at all. So if energy is required and the molecule is charged, what kind of transport? Active. K plus, no energy required. How do you know the difference between whether it's passive or facilitated? Because I'm hearing both. Y'all were right in eliminating active because no energy required. So passive or facilitated? This is charged, so it must be facilitated. Okay. Identify the type of transport that will occur for the following molecules. Cholesterol, no energy required. Tell me about cholesterol. We drew a cholesterol molecule. Well, I did. You remember me drawing a cholesterol molecule for you? And that one end was polar and one end was non-polar. Remember that? But it was kind of what? Kind of big. And it has a polar end. So what do you think is going to happen? Passive diffusion or facilitated transport? Because I see no energy required. So it's got to be one of the two. Passive or facilitated? Facilitated. Nitrogen. Nitrogen is always going to exist as N2. Or a nitrogen with a triple bond. What's going to happen with this molecule? Passive diffusion. Small and it's non-polar. Small. Cl minus, no energy required. This is charged, so it can't be passive, but no energy is required, so it is facilitated. H plus, energy required. This is charged and it requires energy, so it must be active. Not too bad, right? Okay, now take out your eye clicker. Get your best friend out. Let's see, it's so hard for me to see these. Oh, it's gotta be this one. Okay, yeah. Okay, so now, and you might want a calculator. I've got a calculator. Okay, here we go. I'm going to give you 3 minutes. What is the molar concentration of a lidocaine solution prepared by diluting 5 mils of a 1 molar lidocaine stock solution to the mark in a 25 milliliter volumetric flask? The formula you need is on your equation sheet. So 3 minutes. You got a whole 2 minutes to go. Write down your problem so that when you share with others, you can have something to compare. Okay, about 15 seconds left. Take a guess. If you haven't guessed, take a guess. Okay, so turn and talk to the people around you. Okay, y'all ready? Don't forget to click in again if you have not clicked in. Maybe we have way more people than that. Don't forget to click in more than once. How many people did we have? I always forget to look. Okay. All right. So what did you say? You said, most people said E. Very good. It was E. So we had, wow, that's really diverse. Okay. So how do you set up this problem? When you're reading the problem, what formula do you automatically think, oh, I know I need to use this formula? CI/VI is equal to CF/VF, right? Anytime you see a dilution, you should automatically think, I probably will need this formula. So now my initials, what's another word for initial in dilutions? Stock. And then usually we call a working solution or something like that, right? So when I'm reading my problem, how do I know what's my stock? My stock is what is being diluted. So I have here, it's prepared by diluting 5 mils of a 1 molar lidocaine stock solution. So this is my initial or my stock. And then I know I'm going to have a final volume. So this is our final volume. So now I just go ahead and plug it into my formula, right? And I get C1. So see, sometimes I do 1s and 2s instead of initials and finals. That's how I learned. So all you do is plug it in. So we had 5 mils of a 1 molar solution, stock solution, and we made 25 mils of, that should have been a C. Look at that. I even did that wrong. That should have been a C. So this should have been C. 25 mils of some concentration. And so when you do 5 times 1 is 5 divided by 25, you get 0.2. Okay. So what do you think the confusion was in the beginning? Was it not knowing what formula to use, or you knew which formula to use and you plugged in the wrong numbers? What do you think? More formula? Yeah, more formula. So anytime you see the word diluting, right? That's the go-to, like, okay, I know I need to use this formula, right? And then where do you go to find that formula? You go to your best friend and you go to solution equations, right? So it's important to know where to go in your best friend. Get to be really best friends with your best friend. Okay, so this is basically what we were doing just a minute ago. Select the correct statement regarding solutes crossing a cell membrane. So read the statements carefully and evaluate each one. Okay. Make sure you click in. Make sure you click in. All right, so turn and talk to the people around you. "45 seconds." Okay. Almost 5 seconds. Make sure you click in a second time. Okay. So what did we say? Good, good. It is B, okay, and we went up. So when you were looking at all of them, when you were trying to evaluate which one's which, magnesium ions are more permeable than small neutral amino acid molecules. If you're small and neutral, what are you doing? You're booking it across the membrane, right? You're diffusing. What if you're small and charged? Can you go across the membrane? No, you can't. So it would actually be the opposite, right? The magnesium ions are less permeable than the small neutral amino acids, right? We said B was correct. Water molecules are more permeable than sodium ions, and that's true. Water's polar, but sodium's charged, right? Sodium's not getting through. It's just not. Sodium ions, Na+, are more permeable than oxygen molecules. Oxygen is what? Small and what? Nonpolar. So if it's small and nonpolar, it's booking it across the membrane. But my sodium ions, not so much, right? They're charged, they're not getting through. So it's again the opposite, less. Proteins are more permeable than glucose. Tell me about proteins. They're really big. They are really big. And they sometimes, a lot of times, tend to be charged. So, or at least have portions of the molecule that are charged. So it's completely the opposite. They are less permeable than glucose. Okay. All right, so let's go start our last chapter, y'all. You excited? I'm a little sad, a little excited. A lot of conflicting emotions. All right, view, full screen. All right. So acids, bases, and buffers. I love acids, bases, and buffers. This is going to get really, really applicable, especially when we're talking about drugs that are given to someone and how they react in the body and that kind of thing. You really have to understand how acids and bases work. The other thing is we work at a very particular pH, right? We're really close to what pH? Our whole bodies. We're close to 7. We're not quite 7. We're not quite neutral, but we're really close to 7, right? And 7 is neutral on that pH scale. That pH scale tells us about acids and bases, right? So while we're talking about this, I want you to pull out your best friend and I want you to turn to the page that says acids and bases. And I want you to have this next to you, okay? If I have the pH scale, and here's 7, here's 0, and here's 14. What is this portion of the scale? Below 7. If I have a pH below 7, what am I? I'm an acid or acidic. If I have a pH above 7, what am I? I am a base or basic. Okay, how about if you are exactly pH 7, what are you? Neutral. Do you have that information given to you on your best friend? It's on your best friend. I'm not going to take your best friend away. I'm never going to take anything off your best friend. Okay. So when we're trying to think about acids and bases, it's kind of good to kind of have a running tally in your mind about characteristics of acids and characteristics of bases. So let's kind of do that. Acids and bases. Okay. So if we have something that is acidic, what did you tell me about the pH of that solution? It's high or low? So you have a low pH. If you're a base, you have a high pH. And by low pH, we mean less than 7. By high pH, we mean greater than 7. And we'll talk about what the pH scale is next class. Okay. Now, how can I look at a chemical formula of a substance and know if it's an acid or a base? What does an acid do? Do you remember in the last chapter we were talking about if I had this acid, for example, HCl, I'm telling you that it's an acid, and I put that acid in water, and I'm telling you that it 100% disassociates. What does it turn into? Hydrogen ions and what? Chlorine ions or chloride ions, right? So in order to be called an acid, if this is an acid, what does it have to do? Make what in water? Makes hydrogen ions in water. Let me give you an example of another substance, NaOH. Can you take a guess if that's an acid or a base? This is a base. If I put this base into water, what's going to happen? This is a base. Is it going to make H plus? Oh, that's an acid. You can't make H plus. So what's another way that you can split this molecule? Na plus plus OH minus. So bases tend to do what? Make hydroxide or OH minus ions in water. Notice how they're opposites of one another. Okay. Another way that you can define acids and bases that's very similar to this, makes hydrogen ions and makes hydroxide ions, is that acids are something that can donate hydrogen ions in a reaction. Well, if acids donate it, what do bases do? They accept it. Okay, so let's think about some things just in general that are acids and bases that we come into contact. Oh, except H plus. I'm sorry. Yep. I'm so used to. All right, so let's talk about some things that are acids that we interact with on a daily basis. The HCl that I drew earlier, hydrochloric acid, do you know that that's found in your body? Where is it in your body? In your stomach. That is stomach acid. That's why your stomach has such a low pH, because your body produces hydrochloric acid to break down the things that you eat. So stomach acid, right? That's an example. What are some things that we like to eat that are acidic? Lemons, any kind of citrus fruit, right? So citrus. You know what the taste of acid is? Sour. Anything that's sour is acidic. So citrus, who likes salt and vinegar chips? Uh-huh. You like vinegar. That's an acid. Okay, let's talk about bases. Bases have this really unique property in that they're really slippery. So the soaps that we use, are very basic. So our shampoos, our body washes, all that kind of stuff, soaps, they are slippery. Another kind of soap, not really a soap, but sort of a soap, toothpaste is another example of a base that we interact with on a daily basis. And they have cleaners that are either acids or bases, depends, that kind of stuff. But okay, so that kind of gives us a good survey of what's an acid versus what's a base. So let's look at some descriptions and see if we can identify. Neutralized by a base. That's an acid, but let's talk about that. You're right that that's an acid. Let's explain that. If I have, let's say I'm doing an experiment, right? Y'all know I love to do experiments. The only thing better than the sound of calculator clicking is the sound of an experiment happening. And I have an acid, right? And my students are doing an experiment and they need an acid and they also need a base. So I give them hydrochloric acid and I give them sodium hydroxide. And at the end of class, there's leftover acid and there's leftover base. Can we pour that down the drain? Oh, absolutely not. Dilution is not the solution. It's not, okay? Do not pour acids and bases down the drain. And so you tell everybody, okay, put your acids here, put your base there, right? If you've been in a high school chemistry, you've experienced that. So what does the teacher do when you walk out the door? I'm going to teach you. She takes it and she combines the two. What happens? Take a look. Hydrochloric acid is an acid. So if I put it in water, this hydrogen will come off, right? If sodium hydroxide is a base, what's going to come off of the base? What is HOH? What's left? Na and Cl. What did I make? A salt and water. Can I pour that down the drain? Yeah, so all I do is mix acid and bases till I get to pH 7. I have done what's called a neutralization reaction. So an acid, HCl, will neutralize a base to make a salt and water. Isn't that kind of cool? Okay, so we can erase that. But we're going to talk about that later today. Okay. Produces OH minus in water. The base. Has a slippery feel. Base. Donates a proton. Acid. Very good. Very good. Okay. So, that's the other thing I wanted to say. Donates a proton. But I said it was a hydrogen ion, not a proton. They're the same thing. Why are they the same thing? What's a hydrogen atom? Look at the periodic table. A hydrogen atom has an atomic number of 1. So how many protons? 1. It has an atomic mass of 1. Can I have a proton and a neutron with an atomic mass of 1? No. I can have a proton and an electron, but I can't have anything more than that, right? So my proton is all alone. I've lost the electron, right? That's how we get an ion. We lose the electron. If we lose the electron, what's left in my hydrogen atom? A proton. So a proton is the same thing as a hydrogen ion. Okay, so to know that. All right, so now we have this hydrogen ion that we can express as H plus, right? That means it's a hydrogen atom that's lost its electrons. How in the world do a hydrogen ion and H3O plus mean the same thing? Well, if it's an aqueous solution, what does that mean is also there? Water. So if I draw water, How many times have we drawn? I would love to have like a running total of the number of times we draw water in this class. So if I'm going to draw a perfect water molecule, what else am I going to give this water molecule? Lone pairs. Am I done? Why is water so awesome? Yeah, by the end of class, like every day from here on out, I'm going to say, why is water so freaking amazing? And y'all are going to tell me, because it is polar, because it is polar. It's amazing, right? So what does that mean? What does its polarity mean? It means that our hydrogen atoms are partially positive and our oxygen atom is partially negative, right? That oxygen has higher electronegativity, so it just hogs those electrons. So the electrons hang out more with oxygen, making it sort of negative, and they hang out less with hydrogen, making it sort of positive. So now what happens between my water and my hydrogen ion? My ion is positively charged. If I have an ion and something with a dipole, what can happen? An ion dipole interaction, right? Okay, this ion dipole interaction is so freaking strong that hydrogen ion will actually create a covalent bond with the oxygen. So you will end up with H3O+. So in reality, hydrogen ions don't actually exist because they're picked up so quickly by those water molecules and they make H3O+. Isn't that really cool? Like maybe not. I think. Okay. All right, questions about that? All right. So now we need to be able to look at substances and tell, what are they doing? Are they acting as an acid? Are they acting as a base? So we can start to predict their behaviors. So if we look here, we're going to identify the reactant that is an acid. So I'm going to do the acid in red, and the reactant that is a base is going to be in blue. So if something is the hydrogen ion donor, if it is the acid, what do I look for? On the left side of the equation in the reactants, it's going to have more hydrogens than it does in the products. So look at this equation. Which substance, the first or the second, donates a hydrogen ion? So it's going to start out on the left with more hydrogens, and it's going to end up on the right with less hydrogens. So look at H3PO4. What does it turn into? H2PO4. So we go from H3PO4 to H2PO4. Is that a gain or a loss of hydrogens? It's a loss. So this is the acid because it donated a hydrogen ion. Well, if you have something donating a hydrogen ion, something else has to pick it up. What's going to pick up that hydrogen ion? Water. Water starts out as H2O and ends up as H3O. It was the hydrogen ion acceptor. It picked up an extra one. It went from having 2 hydrogens to having 3. So this is the base, and it accepted a hydrogen ion. Isn't that a nice balance? Okay, let's look at the next one. H3PO4, I'll do it in black so that I'm not telling you what's happening, goes to HPO4. Is that the behavior of an acid or is that the behavior of a base? That's a base. That is absolutely a base. So we're going to do it in blue. Why is it a base? Because it accepted a hydrogen ion. So what does that make water in this case? Makes it an acid because it did what? Donated a hydrogen ion. So tell me something unique about water. Water can act as an acid or a base. Isn't that kind of cool? Water just gets cooler every day. So the next thing we're going to talk about is the strength of acids and bases. Now, when we say something is strong, what we actually mean is how easily it can disassociate hydrogen ions or how easily it can pick up hydrogen ions. So, for example, when I talked about hydrochloric acid, right, HCl, what did I draw? I drew that one-way arrow, right? That one-way arrow told me what? What does a one-way arrow tell you in every chemical reaction? Is it going to go backwards? No. So what kind of a disassociation is happening here? 50%, 0%, 100%? This is 100% disassociation. What have we called that in the past? A non-electrolyte, a weak electrolyte, or a strong electrolyte? We call that a strong electrolyte. Well, guess what? Acids that are strong electrolytes, we call those strong acids. Tell me about this water over here. This water is an acid. Is it a strong acid? How do you know that? I'm seeing no's. I love those. Why is it not? I look at that arrow. All I have to do is look at that arrow. And what does that arrow tell me? It's weak. That's what's really nice about the arrow. I can just look at the arrow and I can say strong or weak. But sometimes they're not going to give that arrow to you. And neither am I. So you have to be able to decide, are things strong acids or bases, or are they weak acids and bases? So that's the next thing I'm going to teach you. I'm going to teach you how to determine if something is a strong or weak acid or base. So let me clear myself some room. I'm going to need room over here. So I'm just going to erase this. Okay. So what you will notice is I was super insanely nice. And I put these 6 common strong acids for you. But I'm also going to teach you a trick to know them because it will help you so much. So let's talk about strong acids and then we'll talk about strong bases. So strong acids. There are 2 kinds of acids. There are acids that are called binary. What does binary mean? It means 2. 2 what in this case? 2 atoms or 2 elements, right? What if it's an acid? What does one of those elements have to be? Definition of an acid is it loses a hydrogen ion. So it has to have a hydrogen ion to start with. So one of them has to be an H. So it's going to be an H and then some other element. We'll call it X. Right? That's the format for a binary acid, HX. So now I can have HCl, HBr, HI, HF, H, so on and so on and so on and so on, right? How do I know which ones are strong and which ones are weak? there are 3 strong ones. And the way that I remember this is I say to myself, I bring clay. I is for HI, bring is the Br for bromine, and clay, the Cl, is for Cl. So HI, HBr, HCl are all strong. All other binary acids are weak. So look at your 6 common strong acids, HI, HBr, HCl. These are the I bring clay. Right? So that makes it kind of easy. You have a second type of strong acid. The second type of strong acid, I'm going to erase this, are tertiary acids. What does tertiary mean? 3. So you have 3 or more elements. If you have more than 2 other things that are hydrogen, right? A tertiary acid is going to be H, X, Y, right? Am I going to go to the periodic table to go find this X, Y? No, I have to go where? Polyatomic, poly meaning more than 1. So I'm going to go to my polyatomic ion table. That's where I'm going to find the other half of these tertiary acids. So that's going to be really important when we go to name them. But what do you have to remember about tertiary acids? It's going to be strong if you have 2 more oxygens than you do hydrogens. That's the rule for tertiary acids. So this is for tertiary acids. So let's look at this little chart, our 6 common strong acids, and see if our other acids fit that definition. So if I look here at perchloric acid, how many hydrogens do I have? I have 1 hydrogen. How many oxygens? How many more oxygens do I have than hydrogen? I have 3 more oxygens than hydrogen. Do I fit the definition? Yeah, I have at least 2 more. I have at least 2 more, so that is good. Sulfuric acid, how many hydrogens?
2.
How many oxygens? How many more oxygens than hydrogens?
2.
Isn't this nice? Such a cool little trick. Nitric acid, how many hydrogens? How many oxygens? How many more oxygens than hydrogens? They all fit the definition. Pretty nice, right? So you remember those 2 statements for strong acids, and you've got it. Now, I'm going to give you one other tip for acids. My other tip for acids is that any acid with carbon is weak. Any acid with carbon is weak. So if you see a carbon containing acid, just automatically, that's weak. Oh, that's weak. Okay, so now let's talk about bases. Our strong bases are bases that form with group 1 elements. So if it's a base, give me an example that I've used today of a strong base with a group 1 element. Sodium hydroxide. What group is sodium in? Group 1. And it's a hydroxide because it is contains a hydroxide, so it is a base, right? Okay, so that's true for all of group 1, pretty much, but just go with it. Group 1. It's also true for strontium, barium, and calcium. And I don't have a nice little mnemonic for that. No, I just don't. My other tip for you for bases are if they are weak, if they contain carbon, contain carbon, or if you have NH3. NH3 is an example of a weak base. It's weird. It's a weirdo. It's really a weirdo, but it is weak and it is a base because you can make NH4 plus because it can act as an acceptor. It's just weird. Okay, so now let's see if we can use this knowledge to identify the following, if the following are strong acids. I want you to try not to use this table. HNO2, how many hydrogens do I have? One hydrogen, how many oxygens? Do I have two more oxygens than hydrogens? No, so this is a weak base. No, a weak acid. I don't know why I said base. HNO3, how many hydrogens? One hydrogen, how many oxygens? Oh, now do I have two more oxygens than hydrogen? Yes, I do. So I'm gonna do this. This is a strong acid. Okay, H3PO4, how many hydrogens? How many oxygens? Do I have two more oxygens than hydrogens? No, so that makes it a weak acid. Okay. All right, which of the following are strong bases? What are my rules for strong bases? Group 1 and some of them in group 2. Which one's in group 2? Calcium, strontium, barium. Okay. All right. MgOH2. What group does Mg come from? Group 2. If it's group 2, these are group 2. Are all group 2 strong? No. This is one that's in group 2, but it is not strong. So this is a weak base. NaOH. What group is Na in? Group 1. All of group 1, strong base. FeOH3. What group is Fe in? Oh my God, that's a transition metal. What do we say? That is weak. Definitely weak. Okay. Now, they've changed our wording here. They've said, which of the following compounds completely ionizes in water? What does that mean? Is strong, right? So which of the following compounds we could replace that with is a strong acid or a strong base? It's the same question. Lithium hydroxide. Lithium is in what group? Group 1. So a group 1 metal with a hydroxide is a strong base. So we can go ahead and circle that one. That one's good. H2O. I'm going to give you a hint. Scroll up to the top, like you have to scroll with your paper. It's funny. What did we do with these yield signs? Are they a one-way? No, they're a two-way. So what must be true about water, either as a base or water as an acid? It's weak. So you could write next to it weak acid / weak base, right? Benzoic acid. Why is it weak? It is a weak, and it's a weak acid because it's carbon containing. Not too bad, right? Now, I'm going to, before I do that, I want some space to write. You can go to that page. I just need some space. Okay, one of the other things that you have to do is you have to be able to name acids. Not really bases, you just say hydroxide. It's pretty easy. Acids are kind of more of a pain in the butt. But I love the names of acids. It's kind of fun to name acids. So remember how I told you there were two kinds of acids? There are binary acids, and what's the other one? Tertiary acids. Okay. Binary acids are easy because they're always going to be in the form of H and then some element, right? So think about how we used to name compounds. We're going to name them kind of in the order that they go. So what's that first element? Hydrogen, right? First element's hydrogen. So we call it hydro, right? That's our hydrogen part. So every single binary acid is going to start with hydro because it can only be two elements and one of them has to be hydrogen. Then you're going to have a space, and that is going to be the name of the element. So this is the root of element name. Then you're going to end it in IC, a space, and it's going to be called acid. So if I had HCl, how would I name that? Hydro. And then I'm going to say chlorine, but I'm not going to give that end, right? If I go and find chlorine on the periodic table and I want to name the ion, how do I name the ion? What do I end it in? IDE. So instead of doing IDE, what are we going to do? IC. So I'm going to go hydrochlor. Instead of IDE, I'm going to say IC. So there's the root of the element name, and I'm going to end it in acid. So how about HI? If I go and know I'm going to name it hydro, right? Now the I, if I go find it on the periodic table, that's iodine, and I would name that IOD. Iodide, IOD, but do I put the IDE? No, I'm going to put hydroiodic acid. They're just fun to say. They're just fun to say. Hydroiodic acid. You sound like so fancy, right? Okay, so that's binary acids. Binary acids are relatively easy. Now, tertiary acids. Tertiary acids, I want you to remember a phrase, okay? The phrase is ick. I ate a humongous bite, right? Ick, I ate a humongous bite. Why is that important? Because tertiary acids are always a combination of hydrogen. Tertiary acids are hydrogen plus a polyatomic ion. So go look at your polyatomic ion table, like all these papers. Go look at your polyatomic ion paper. Most polyatomic ions are going to end in what two endings? Either IDE, ITE, or ATE. Do you see that? So most of the polyatomics end, so this is the poly ending. Depending on what the polyatomic ion ends in, tells you how you name the acid. So if it ends in ATE, now you're going to end it in IC. If it ended in ITE, you're going to end it in OUS. Isn't that neat? So the other way, the other one that I know is I went to chemistry class, went to chem class, and got 8 ick-itis. I got adic-itis. Sounds like you got some terrible disease, right? Oh my gosh. Me in this chat box, adic-itis. So I-T-O-U-S and A-T-E and I-C. It's the same thing. If you end in I-T, oh, it's I-T-E. I can never spell I-T-E-O-U-S, right? If your polyatomic ends in O-U-S, I'm sorry, good Lord. If your polyatomic ends in I-T-E, you change it to O-U-S. If your polyatomic ends in A-T-E, you change it to I-C. It's the same thing. It's just two different little mnemonics to remember. Whatever works for you, okay? So now, after I've taught you all that, look on your best friend. Look on your best friend. What do you have on your best friend? If you have something that ends in IDE, what ends in IDE? Only what? Binary acids, right? Binary acids have those ions that come from the polyatomic ion table. Binary acids have the element that comes from the periodic table. So it ends in IDE. So if it ends in IDE, all you do is add the hydroic acid, hydro whatever ic acid, right? So that's binary. ATE and ITE are what? Tertiary acids. So here I'm telling you, if it ended in ATE, what do you change it to? IC. If it ended in ITE, you change it to OUS. So if you forget the rules, are you in trouble? No, what do? Go see your best friend. Your best friend has your back, okay? And I'm trying to. So let's name and write the formula for the acids that are formed from the following ions. What we haven't talked about is how to write the formulas. So just like an ionic compound, your final formula must be a neutral compound. So if I have iodide, that's the ion of iodine, how many hydrogen ions do I need to combine to make a neutral substance? If H plus has a charge of +1 and I minus has a charge of -1, one of each, right? We're just making a neutral compound, just like we did in the past. Okay. Now, how am I going to name this? Is this binary or tertiary? This is binary. So what do I start with? Hydro. Then we name the ion, but we don't put IDE, we put IC. So hydroiodic acid. We did that one. Oops. Oh well. Be all right. Okay, how about B? Perchlorate. Now, sometimes I give you the name on the exam and sometimes I won't. Sometimes I'll just give you the formula. Like I'll just give you this. So what would you do if I just gave you that? Go to your best friend, go look at your polyatomic ion table and get the name. So the name ends in ATE. So all we're going to do is if it ended in ATE, we're going to change it to IC. But do we put hydro? No, because it is a tertiary acid because we got it from the polyatomic ion table. So we're going to call this perchloric acid. Aren't these fun names? Okay, acetate. Tertiary or binary? Tertiary. So we're going to get rid of the ATE and we're going to add IC and we're not going to add the hydro. So we're going to call this acetic acid. Oh, we didn't write formulas. Oh, y'all, we didn't write formulas. Okay, so let's do the formula for B. What do we write a formula for B? How many hydrogens do I need to balance the charge? How many? What's the charge that I need to balance? A -1. So I need a +1. So how many hydrogen ions? 1, HClO4. Okay, how about acetic acid? I have a charge of what to balance? -1. So how many hydrogens do I need? 1. Now, usually we write the hydrogen first, and that's fine. But in this case, the hydrogen actually attaches to this oxygen right here on the end. So for acetic acid, we tend to write CH3COOH, but it's the same thing as HCH3COO. It's the same thing, right? We're just expressing it a little bit structurally when we put the H on the end. Okay, so it really doesn't matter. I don't think your book cares. If it does, tell me. If it does, tell me. Okay, pretty good on that. Now I'm going to tell you, if you want to do well with this, you need to practice it. So I would go to the end of the chapter and I would go to those extra problems, and anything that said name this or write the formula for this or whatever it is, do the practice. The more you do, the better you're going to be at it. All the odd numbered answers are there. If you want to attempt the even ones, if you write them out, take a picture of your work and send it to me, I'll check it for you. And I'll tell you if you're right or wrong. Now you can't email me and say, Dr. B, what's the answer to number? Can't do that. But you can take a picture of your work, send it to me, and I can check it. Okay? All right. Okay, now, this is fun, right? I love acids and bases. I don't know why, I just do. So the next thing is neutralization reaction. And y'all kind of know about this, right? Because we kind of talked about this first. So in a neutralization reaction, what do we make? Right? When that teacher poured the sodium hydroxide and the hydrochloric acid, what did that teacher make? A salt and water. So you're always going to make a salt and water. But sometimes you also make CO2. If you had something that started with a carbon, like look at B. Do you see in B? You see how I have a carbon? I know that B, I'm going to make a salt, water, and carbon dioxide. I know in A, there's no carbon, so I'm just going to make a salt and water. See the difference? You can see that right away. So let's try this. We're going to have HNO3, and I'm going to leave off the states of matter. Well, your book wants them, so you should put them. I'm just afraid I'm going to run out of room. Okay. When I'm looking at this, I know I'm going to make a salt and water. So look at your original reactants and take out the things that make water. So from HNO3, what am I going to use for water? That's an acid. What does an acid do? Y'all right. That hydrogen's going to leave. And then in MgOH2, I put, look at me, that's terrible. Terrible. What part of that molecule is going to become part of water? The OH. Okay, so I know I'm going to take those things together and I'm going to make H2O. What do I have left? I like to start with my metals because I know I'm making a salt, right? So we know a salt is a metal and a non-metal. So I'm going to take my metal, that's magnesium. And what's it going to combine with? In this case, it's not a non-metal, it's a polyatomic ion, NO3. So Mg, NO3. Now we got to be careful. Why do we have to be careful? First, before you try to balance, is my formula correct for MgNO3? It's not. Why not? What's the charge on Mg? 2+. What's the charge on NO3? 1-. So if I do the crossover, that ends up a 2 down here and a 1 down here. Can I just go ahead and pop my 2 in right there? No. What do I have to do? Put NO3 in parentheses and put a 2. Okay, now I need to check, am I balanced? No, I'm not. I'm not balanced. Now, like, don't try to balance atoms. I know you want to do that. Balance units together. So look at the NO3. In my reactants, how many NO3 units do I have? Only 1. How many do I have over here? 2. So if I put a 2 here, now I have 2 NO3 units, but I also did 2 of these hydrogens, and I've got that combining with 2 of these hydroxides. So how many molecules of water am I going to make? 2. Am I balanced? Yes, I am. So do you see how I kind of think about balancing things differently for this? Keep things together that stay together. Okay, let's do B. Can I erase A so I have room? Yeah. Let's do B. Because B is going to be special. What did we say about B? It's got carbon. Ooh, I think I forgot to put in my states of matter on the products for A. What should my states of matter for the products be? Aqueous. And then water is what? It's a liquid. But everything else is aqueous. Okay, don't let me forget to do that on this one. So we have hydrochloric acid plus NaHCO3 solid. Okay, what's going to happen? I know I'm going to make water, right? So where am I getting water? I'm getting a hydrogen from my acid. What is going on over here? What else do I need to make water? I need another hydrogen. And I need how many oxygens? 1 oxygen. So I'm going to make H2O. Now, I need to make what else because I have carbon? CO2. So I'm going to pick up the carbon and I'm going to pick up what? 2 oxygens. So from that, I'm going to make CO2. So I've used up really all of them. What do I have left? I need another color. I have left chlorine and sodium. What does that make? Sodium chloride. So now, states of matter and balancing. Water is a liquid, CO2 is a gas, and because we did all this in an aqueous solution, NaCl is aqueous. Are we balanced? And look at all those pretty colors. Kind of love that, right? Okay, I think I'm going to stop there. Any questions? I hope you have a very, very happy Thanksgiving. Please use your time wisely and please study. I know I will be enjoying Thanksgiving, but also working. So I'm going to highly recommend you do the same. Anybody on Zoom need anything? Happy Thanksgiving. Thank you, Abigail. All right, I'm gonna go ahead and end the meeting.